So, okay, so that's the last lecture. So the lecture where I really want to, give you a taste of this good quantum LDPC code I was mentioning before. So before that, let me review again quickly what we said this morning. So we had the surface code. So it's defined, on this kind of generalization of a graph, where now you have vertices, you have edges, and you have squares. Okay, so we put the qubits on the squares, and the way we put constraints, so the constraints are always around vertices. And we have two types of constraints, Z and X. And the X, they will be around the red vertices, so this kind of, with this kind of pattern. And the Z will be around blue vertices. And what happens is that if you look at, adjacent generators, so adjacent vertices, what will happen is that the support of the two generators will always overlap on two positions. So either a column, like here, and then they commute, or a row, okay? Like, I don't know, like here. And then they commute. And, so this thing, in a kind of well-defined manner, it's really the product of two repetition codes. Okay, so if you see the repetition code, as you know, a code defined on a graph, 1D graph, that, it's a cycle like this, with, constraints that are just checking that the two consecutive bits have the same value. Then there's a way to define a product of two things like this that gives you that. Okay. And so what do we want to do now if we want to have better quantum LDPC codes? Well, the idea is to kind of, replace this by good classical LDPC code, and then, take the kind of the product, or you go from here to there. So if we want to replace this by a good classical LDPC code, what we need to do, if we want to follow the recipe that I was giving yesterday, we need to modify this graph so that it has a larger degree, okay? Because here the graph has degree 2, so the constraints that we can put, they just look at 2 bits at each time, and it's not enough to get good expansion properties. So what we want to have is like a better graph with a slightly larger degree constant, but more than 2, so delta. And what we want is that for each vertex, at each vertex we impose some constraints, and the constraints will be that the words that we see on the coordinates that we see around the vertex. So x, v should belong to some small code C0. Okay, so that was. Yes.
So just going back to this picture.
Yeah.
So qubit sits on the edges, right?
No. So qubits here, they sit on the faces, on the squares. Okay.
Qubit sits on the
they are on the, yes.
What sits on the edges?
Nothing. So nothing on the edges, qubits on the squares, and the constraints, the generators, they sit on the vertices. Okay? So it's always like this for these constructions. Qubits on the squares, and generators or constraints, they sit on the vertices. So this is not the standard way that people present the toric code. So usually when we present the toric code, we say the qubits are on the edges, and there are two types of generators on the plaquettes and on the vertices. This is not what I'm doing. I'm doing something slightly different that gives you basically the same code, but in this picture, you can generalize it to give good quantum LDPC code. With the other picture, it's not so easy. Yeah.
So why is this graph bipartite?
Which one?
The lower one, yeah.
It's not needed. It's easier when you take it bipartite. Otherwise, it's a bit. This one. This one. It's drawn as bipartite. Do I need that? So I don't need that. Where did I use it? It's kind of hidden. I use it when I count how many, how many edges there are, and counting is it's not much easier, but it's slightly easier, and for the program code, it's also easier. Yes. No. So CSS is really, so for, yeah, no. Okay? Okay, so in the quantum case, what I need, so here I have, for the story code, I have this grid, or this channelization of a graph, and I have the local codes. So the local codes will be just, these things of size 4, so this 1111, and 000. And this I can understand it as a product of, 11 and 11. So this, somehow the local code here is really, C0 times C0, where C0 is just the code with two code words, 00 and 11. Okay, so that would be the code that is useful for the repetition code, and when I move to the surface code, I use this code instead. So now if I want to generalize this to have like a better code, I need two things. I need to tell you which kind of grid I take, what is the thing that will replace the graph. So I need something with degree more than 4. And I need to tell you what the constraints will be. Okay? So this is the part where it gets a little bit tricky. So I need to define first the complex. So the complex is this combinatorial object with vertices, edges, and squares. So the way we can define it is by taking a group. So we'll take a group, G, not to be confused with a graph, G. It's the same notation, I'm sorry, but just the standard thing. So now this is a group, G, and I need to take, what I will take two subsets of G. Okay, group G, and I will take subset A of G and a subset B of G. And these things will have size delta. So these things will tell me how I get my edges. Sorry? Yes?
A is not a group.
A is not a group. So for instance, the group that would correspond to this thing, to the story code, it would be Z over NZ. So integers mod n times integers mod n. So it's a product of two groups. So this would be my G. And in this case, okay, so an element of G would just be, some G in G. What does it look like? It's just, two numbers. G would be some P, Q, where both P and Q, they are numbers between 0 and n minus 1. Okay, and okay, so the small n here, or maybe let's call it, I don't know, capital L, L, then basically I have, this would be somehow L, I think. So you have a group where basically the first coordinate tells me what is the vertical value and the horizontal value. Yeah.
Can you remind us of notation
these are just integers modulo L. So these are just, 0, 1, L minus 1. And you have addition in this, mod L. So this would be the group for here, and the A and B, the two sets would be, A would be just, would consist of two elements, because in this case, there would be two elements, so there would be 0, 0, 0 thing, and I guess 1, 0, and B would be 0, 0, and 0, 1. So I need to explain to you how we get things from this, but okay, this is an example. So G is something like this, A and B or things like that. Okay, so I have this group, I have these two subsets, and now I need to define this kind of object. So I need to define three things. I need to define vertices, I need to define edges, and I need to define squares. So the vertices, what will they be? There will be 4 copies of G. So I take 4 copies of G. So this is somehow, in some way, the kind of a generalization of the bipartite nature of this thing. So this thing is bipartite. Somehow you have 2 copies of the vertices. In the quantum case, usually 2 translate into 4, so I have 4 copies. So these are 4 copies of the elements of G. So you have a set labeled 0, 0. So we have 4 sets of elements of G. 0, 1, and then 4th set, 1, 1. So all these guys, they contain, these things, they are all a copy of G, of the group. So these are my vertices. Yeah. So the notation is just, it's just a label to distinguish these four things. So here, when you have a bipartite graph, you can say, okay, the left vertices and the right vertices. Here I have 4 copies, so you could say, okay, left, right. I just need a label for distinguish these 4 types of vertices. Okay, but inside, so any vertex of this form in my complex, it will be some labeled by some G and some ij. So G is an element of the group, and ij can be 0 or 1. Okay, so the number of vertices is 4 times the cardinality of G. So these are the vertices. I need to tell you what are the edges. So I will have 2 types of edges. A little bit like this. I will have horizontal edges and vertical edges. So I will call them A-type edges and B-type edges. So edges, so you have edges of type A. So what is it? So this will be vertical edges in this picture over there. And basically they relate. So in the construction I will take, I will also ask that, if I will take A and B to be symmetric. It helps a little bit. What does that mean? It just means that if the element small a belongs to set A, then A inverse also belongs to set A. Okay, I have a group, so every element of the group has an inverse. I ask that, the subset A is symmetric like this. Okay, so what is an A-type edge? So the edges of type A, they will go from this place to this place, or this place to that place. And they will relate, or they will relate an element G here with an element A times G in this thing. Okay, so G is a group, so I can multiply any element of G of the group, by some element A.
So what is A in this case?
A is anything that belongs to capital A. Okay, so these guys, so they will always relate some G in, what is it? Some ij, I'll say 0, 0, will be connected to aj in 0, 1. For all A in A, and for all G in G. Okay? Say that again? The multiplication is the multiplication in a group. I have a group. So it can be a general group. So it's just, you have a group, you have a group structure, you have a multiplication in a group. So in this case, this example, the group was just integers mod n or mod L. So what I call multiplication would just be addition because it was like an additive group. But in general, we will want non-abelian groups, so it's better to use multiplicative notations. Yes?
I just want to make sure that I understand because it seems that you're going to normalize it. But when you're talking about the variables in A, there is only the 0, which is 0 times 0, or 0 times 1 because this is the two variables that you define.
So
And not also 0 times, not times, but 0, 2, 0, 3, 0, 4. Only two variables. You only have two variables in A.
So before, in this example, you mean? Yeah, so in this example, A had cardinality 2, so there were only 2 elements. So there were 2 edges. And basically, you had one edge. If you start at this point is G, somehow, so you can move up or down. Okay, so moving up would be, maybe you don't do anything. And moving down, it would be like 1, 0. You move 1 on the first coordinate, 0 on the second. And moving down would be, if I want something symmetric, it would be -1 and 0. So, no, so it's a small g. So g here is an element of the, yes. Yeah. So these are vertical edges, like this. So I have these both in here and in there, okay? So g from 1, 0 goes to 1, 1. And I have also horizontal edges, which are type B. So these are horizontal. So what do I want to do now? I want to go from G to, in this set to G to another group element in that set. And what I will do, I will multiply with an element of B, but I will multiply on the right of G. So I will go from G to G times B. Okay, so on one side, when I go up or down, I multiply by A on the left. When I move left or right, I multiply by B on the right. Okay, that makes sense? So G in 0, 0 is connected to G times B in set 1, 0. And this is for all B in the set B and all G in the group.
Before you notice that A became 0, 0 and 0, 1, so?
Yeah, so okay. Maybe I should have said, maybe, yeah. Yeah, so if I want to stick to this notation, I should have said, yeah, 1, 0 and -1, 0. Yeah. Yes?
How do you define the elements in the set 0, 0, and 1?
How do I define which elements are in A?
In the set 0, 1,
All of
the
G.
set 0, 1.
All of G is here. There's a whole copy of G everywhere.
Okay, and just define which elements are connected.
And I define now which elements are connected from between here and here by saying that you move from an element G to an element A times G. You multiply by some A. Okay, so this gives me my edges. So you have the vertices, I have the edges. And now what I have in addition is that I will have squares. So why do I have squares? Because if I move first right with an element B of the set B, I arrive at GB, and now I can move up with an element small a of set A. And where do I land? I land at A, G, B in this set. Okay? But I can also go first with an element of A, so I move up with an element of A, with this kind of blue edge, and then I move right with a red edge. And if I move right with the same element B, I also land in AGB. With opposite order, but not these things. The point is that because the multiplication by A is always on the left and the multiplication by B is always on the right, this thing is always the same. And these things commute. So basically, you can first go through this path and then here, or first to the right and then up, and you commute and you always arrive at the same point. And this is kind of the crucial thing that happens in this construction. So this defines squares. So the squares, they are all of this form. So you have some G in 0, 0. So you have 4 vertices that define the square, AG in 0, 1, AGB in 1, 1, and GB in 1, 0. Okay, so you can take the set of all guys like this with any element that you want in the first set, and then any A and any B, and you get the squares. So this is called the left-right Cayley complex. It was first introduced, so it has appeared in, kind of appears hidden in all the constructions of good quantum LDPC codes. It was the name of left-right Cayley complex. It appeared in a paper by Irit Dinour and the other people.
So let's see, what is the thing maybe?
Yeah.
Leverrier.
And the fifth one, and Leverrier maybe, where they use the same thing to look at classical codes with good special properties. So that's the complex, that's the thing. So this is our new object. So this is what will replace, this grid, okay, in general. And now we'll do the same thing. We'll put the qubits on the squares, and we'll put the constraints on the vertices. Okay? So now, yeah. So in the case of the surface code, everything was kind of easy to picture. You can picture everything at the same time. You can look at a vertex, and you can look at its neighborhood. So each vertex around it has 4 squares. Here it's a bit more tricky to visualize what's going on, but we kind of need that. So what I want to show you is what does the neighborhood of a vertex look like? Okay, because we want to put the qubits on the squares, we want to put the constraints on the vertices. So on each vertex, we need to say, okay, what are the squares that this vertex sees? And how can we put constraints in this thing? Okay, so what I want to look at is I want to look at an element. So I take an element G in this set, okay, and I want to look at so it's a vertex, okay, this is a vertex. And I want to look at its neighborhood. Neighborhood meaning what are the squares that are incident to this thing. Okay, so if I'm at a vertex G, what are the squares that touch this G? Well, all the squares, they are defined by, you need to make 2 choices. When you already know G, you need to choose some A and to choose some B. Okay, so a square is labeled by an element A and element B. Okay, so the squares around this vertex, the squares are labeled by some couple AB in A times B. Okay, so one way to picture this, these squares is really by, say that again? The squares around the element G. So around each element, the squares, you can label them by, a matrix, if you want, where you choose some A and you choose some B, and for each couple AB, you have some element, you have some square. Why am I doing this? Is because, exactly as in the classical case. So in the classical case, we had these graphs like this, and then we wanted to say, okay, around each vertex, I have delta edges, and so I want to put the constraints corresponding to a code of length delta, but somehow I need to tell you how I order the edges around the vertex, tell you what is the code exactly. Okay, I need to fix the labeling of the vertices. here is the same. I need to fix a labeling of the squares around the vertex. Okay, so around element G of 0, 0, I see something like this. And now I want to see, okay, what, if I look now at an element GB in 1, 0, so I look at a neighbor of this thing in this graph. So now I look at the element GB in 1, 0. What are the squares that are incident to this thing? So again, the squares, maybe so you have many, so it's a matrix. Here also. So again, this matrix, I mean, it will be these two sets. They will be again isomorphic to A and B. But so if I have AB here, so that's this square. Here, if I look at at the column B minus 1, so the inverse of B, in that column, if I look at row A, I will have a square, and this square, so it will be the square that contains, so what will be the square here? It will be the square that contains GB in 1, 0. It will be the square, so in 0, 0, it will correspond to GB times B minus 1, 0, 0. So, but this is G in 0, 0. And then I don't know, then it will be AG in 0, 1. It will be AGB. It will be AGB in 1, 1. So the square that I see here is the same square that I see there. Because this square is really the square that I have here. And actually, the same thing happens for all the column, all this column. So for this holds for any A that I choose. So actually, the whole column corresponding to index B will coincide, will contain the same squares as the column that is indexed by B minus 1 here. So what this means is that if you have two neighboring vertices in this graph, and you look at their neighborhood, so a neighborhood meaning the squares that are incident to these two vertices, they will share a column. Okay? So this this can remind you of what is going on here. So here, if I have these two vertices, the blue and the red one, and you look at their neighborhood, they will share this column. Okay? So here is the same thing happening. And if you look at an element here, as at some vertex AG in 0, 1, you look at its neighborhood, it will also be like a matrix like this, of squares. And now what will happen is that if you look at the row corresponding to A minus 1, then this row, the squares that are in this row, they will be both in the neighborhood of this vertex and in the neighborhood of that vertex. Okay, exactly like for the surface code or the toric code, if we move up from one vertex to the other, the set of squares which are incident to these two vertices, they share a line or a row of squares. Okay? And so this property will hold everywhere in this thing. So everywhere in this thing, whenever in the graph you have two vertices which are adjacent, it means that if you look at the squares that are incident to these two vertices, they will share like either a row or a column. Okay, so that's a property of this square complex, of this left-right Cayley complex. And now I want to exploit this property to tell you what are the generators, because now if I want to get a quantum code out of it, I need to put generators, okay? And so I need to say what are the X generators and what are the Z generators. And I want to exploit this thing. So what I will do, I will put X generators around these vertices and around those vertices. And I will put Z generators around these vertices and these vertices. Okay, so it means that I will define generators. For instance, the generators here, so they will be of X type, so they will be a product of X type polymatrices. I will define such generators for every G, a bunch of those for every G. And so for every G, I will define generators with support entirely on this set of squares, okay, and this set of qubits. And basically what I need to do, so now, I will have like an X generator here and a Z generator there. And I want these two things to commute. This is, I want, quantum code, I want X generators and Z generators to commute. And I know that the support of the two generators, it will overlap. It will overlap exactly on a column. Okay, so what is important now is that the generators that I take, I make sure that, on this column that is shared by these two things, they should have orthogonal support. Okay, this is to make sure that the two generators commute. Okay, so how do I do that? Well, I will use the product codes that I had yesterday.
But from the vertical, I don't have to worry because they are all X, or they are all...
No, so here they are all X in this part, because this is 0, 0, so I put here they are Z. So what will be the support of the generators? So there will be many generators for each square, each vertex. So I will take the generators around this vertex. I will ask that the support of the generators correspond to a code word the support of the generators will be code words of a product codes. Of product code CA times CB. So let me remind you what this means. So CA times CB, so okay, A and B, they are both of size delta. So A equals B. So I will pick two codes, two classical codes, CA. It will be a code, classical code of length delta with some rate and some distance. And I also take CB to be a different code with a different rate. So what I will do, I will take CA of rate rho, and I will take CB of rate 1 minus rho. It has some distance. I don't care about that for the moment. So I take CA and CB, two codes of length delta. And the product code, this thing, this CA times CB, just means, if you remember, so it means that it's, words of zeros and ones, but every column should be a code word of CA, and every row should be a column, a code word of CB. So I do that. So I take, two codes like this, and then, all the generators, they will be all the code words or basis of the code words of this thing. And in that set, so the generators here, their support will be, so we want something which is orthogonal to that. So the X generator, they will have some value in this column. So what we want is that the Z generators on the same column, they should have they should contain a code word which is orthogonal to this one. So the way to do that is by taking, the dual codes. So here I will take generators such that their support corresponds with code words of CA perp times CB perp. So CA perp is just the set of all the words which are orthogonal to everyone in CA. So that's all. So that's what I'm doing for here, and the blue here is also the same. So I take CA perp times CB perp. And for the first one that I didn't draw, for the one in 1,1, I take CA times CB. And in this way, for every two adjacent vertices here, they share this column. So one will see a code word of CA, one will see a code word of CA perp. So they will be orthogonal, they will commute. For two adjacent vertices, like vertically, they will share a row. This row will be the same. So on this row, you will see an X-type generator that corresponds to a code word of CB. And here you will see a code word that corresponds to a code word of CB perp. So they will also commute. They will be orthogonal, they will commute. So this is what we had also for the toy code. So for the toy code, it was really easy. So we had CA and CB, which were just the repetition code of length 2. So just one non-trivial code word, 1,1. And in that case, it turns out that CA perp is also equal to CB perp, which is also equal to CA, the same thing, because 1,1 is orthogonal to 1,1. But in general, you want something, you want to put like a more complicated code here, and here you want to put the dual of this thing, the thing which are orthogonal. And so if you do that, what you get is you get a well-defined quantum code. Okay, you get a well-defined quantum code because everything commutes. It's an LDPC code because all your generators, they have weight at most delta squared. Okay, all the generators, they have weight, they have support inside one of these things. So these things have size delta squared, delta times delta. So they have constant weight. And then, so this defines a quantum LDPC code. So what is the dimension of the code? How many qubits does it encode? So that's not complicated to see. So what's the dimension? So K, it's at least, so the number of qubits minus the number of generators. So what is the number of qubits? So the qubits, I said they are on the squares of this left-right K complex. So this is the number of squares. So how many squares do I have? So for every element, these four sets, for any G in this thing, around it has delta squared squares. So the number of qubits or squares is just the size of the group, a choice for G and a choice for A and a choice for B, so delta squared. The number of constraints, it's at most, because maybe they are not all independent, but at most. So where are the constraints? They are around every vertex. So how many vertices do we have? We have four G vertices. Okay, 4 copies of the group. And for every vertex, I need the number of independent generators. They correspond to a basis of this thing, of CA times CB. So what is the size? What is the dimension of this? The dimension of product code is just the product of the dimensions. So it will be the product of these two things. So it would be delta squared rho 1 minus rho. Okay, so the rate of the code, which is K over N, the number of logical qubits.
Why 1 minus 4? Why not just delta squared?
So delta squared? No, because so the generators, they just correspond to code words of this thing, CA times CB. So this is not the whole space. So I just need to count the dimension of this thing, which is this. So the rate of the code is at least, so if you do the computation, it's just 1 minus 4 rho, 1 minus rho, and this is 1 minus 2 rho squared. So this rate, so as soon as rho is different from 1/2, and this rate is positive. So you have something with a linear number of qubits. So in the case of the surface code, CA and CB, so the rate is 1/2 because you have just, you have the code word 0, 0 and 1, 1, and you don't have 0, 1 and 1, 0. So for that case, the rate that you compute like this looks like 0. Turns out it's not completely 0 because there are some redundancies in the constraints. But otherwise, if you take any other value for rho, and you're sure that the rate is positive. And what I will not explain is that, then you can do the analysis, and you can show that the distance, so if you have a good expander, so if the complex that I define, in particular, if the two graphs, the vertical graph and the horizontal graph, they are both classical expander graphs, then you can show that the distance of this quantum code is also linear in n. The proof is not that complicated. It follows the same thing as in the classical case. It's a bit more tricky. But I will not go into details. It's not that complicated. So really, yeah, the object, so I don't know what you think, but this construction, okay, it may look a little bit scary, but it's not that complicated, I think. And it's kind of amazing because for 20 years, people have looked for this. People had no clue whether these good codes could exist. And in the end, they're not so complicated compared to what people have tried before, which were much more involved. So I think this is it for me. If you have any questions, please. Yeah, so many measurements, no, it's not that complicated. You can just do, you do many gates. This is not a problem. What is more problematic is what you said, the other thing, is the connectivity that you need. So you basically, so in the surface code, it was very nice because every qubit just talks to its neighbors. Here it's not the case anymore, so you need long-range interaction. So you need to be able to either move qubits, swap them, or you need to be able to do long-range 2-qubit gates. So for super connecting qubits, it's not so easy. But if you take ions, or if you take Rydberg atoms or photons, in principle, you could do that.
But the stabilizer apparatus model.
And the stabilizer, yeah, so true. The stabilizer are products of more than 4 qubits. Nobody has really tried to compute the numbers that you need there, so the size of delta. We suspect is quite high, probably like 100, I don't know. Can be quite high. So this construction alone, yeah, it's true that the stabilizers, they won't have such a small support. But then, there are tricks, and there's a paper by Matastings where he shows that if you take any good code with large weight stabilizers, there's a way to kind of transform this to reduce the weight of the generators without degrading too much the parameters. So there are tricks to do that. We have not looked at that. And these are just the first, yeah, but this is true, it's a good point. But this is just kind of the first constructions that beat, the square root n bound for the distance. So for like 20 years, nobody knew whether this existed. Now we know that they exist, and now probably it will be much easier to find new ones. Once you know that something exists, it's easier to, probably.
The thing that we change from the surface code,
Yeah.
try to get that the connectivity of each.
Yeah.
But somehow it does not appear in the rate. The surface code is
So it does not appear in the rate, it appears in the...
different from this general structure in delta, but delta is not in the rate.
Yes, it appears in the bounds for the distance. It's just that here it's kind of a very degenerate thing where, delta is equal to 2, and there's no choice for the CA and CB, there's no choice anywhere. Yeah.
Because if delta is 2, you cannot find any draw.
Yeah, no, exactly. If delta is 2, then, the dimension, if you want something non-zero here, it can only be 1 or 2. 2 is a trivial code where you have everything. 1 is just the repetition code, and then you have only one example. It's just, yeah. And then, so that's one part for the dimension, it doesn't appear too much. But then for the distance, what you need is that the graph, the underlying graph that is hidden there, it has to be an expander graph. So you need expansion. But the graph that we have here is just, the vertical graph is just a cycle, just a repetition, just like, a circle. So it has no expansion, it has no good properties. So if you want to have good properties, you need delta to be larger than 2.
Did you think about how to generalize the left-right scale product to something that maybe would be have more dimension? If you want to, I don't know, think about other placates than squares.
Yeah. So yes. So in principle, you can generalize to other things, to even larger dimensions. So you can take, several sets, A, B, C, D, and but then you need to find a way, to have this kind of commutativity property. You need to go from G to AG to AGB, and you need this kind of commutativity. So you can do that if you take like an abelian group, and
then you don't have the expansion.
But then you don't have the expansion as good, yes. And if you don't take an abelian group, it's more tricky to get something more than 2. But in principle, yes, you can do more than 2. You can do something else than squares. As I said, this is the first construction. Probably there's a lot of room to change that.
I guess you can also ask him if I compare it again to classical communication, and one of the reasons that LDPC codes are so popular is that both we have high rate, and also because the error goes down exponentially with them, which is not something that you have for every error correction code. Now in the quantum case, if you look at some error model, how does the error behave? How does it go down with them?
Yeah, so for these things, if you have enough expansion, we know there are good decoders, that correct like a constant fraction of errors. So we know that below this thing, we will correct everything. So below, I don't know the fraction, but below like 1% of errors, you know that you correct everything, because the distance is like a constant times n.
But you cannot say something about the error for a given noise model. So when it's random, and the number of errors is random.
Yes.
Yeah, but it's even, you can. No, because we can.
You know that with high probability, your error will be just spread uniform about your graph, and then you will have a lot of clusters of small errors, and then you could just pick them.
How does it behave with them? Is it exponential?
Yeah, I think so.
Yeah.
No, it's exponential.